Hello friends, welcome to my channel again. In today's session, we are going to study Suzuki Kasami algorithm. We know that there are three types of clock synchronization: physical clock synchronization, logical clock synchronization, and mutual exclusion clock synchronization. In mutual exclusion clock synchronization, shared resources are accessed by multiple sites. So sometimes there might be conflict may get arised due to the concurrent accessing. We know that in database management system or in operating system there is a concept of shared memory which is resolved by semaphores. So in such a critical section, when multiple sites work together concurrently, so there are chances that some conflict or data inconsistency may happen, which may result into creating issues in the shared memory or critical section. So Suzuki Kasami algorithm basically helps us in the scenario where multiple sites are accessing the critical section. This algorithm is a decentralized algorithm which is based on token. Unique token is shared between the sites. Only one site will be having that token with it if it wants to execute the critical section. If the site is not having token, it cannot enter inside the critical section. Before the algorithm begins, token setup is done. A token is initialized and assigned to one process in the distributed system. The process will maintain three things. First thing is going to be request numbers array. Second thing is going to be last satisfied request numbers, and third is queue. That queue is used for holding the pending request from the processes. Let us see this diagram. One distributed environment is shown. In that environment, 5 sites are working together. Site number 0, 1, 2, 3, 4. Initially, we can say that site 0 or process 0 contains the token. Now, at process 0, Rn is request numbers array, Ln is the last satisfied request numbers, and Q is used for holding the pending request from the processes. Now let's try to understand what these arrays are. Now suppose here process 0 is holding the token. So probably it may happen that other processes like process 2 suppose wants that token and it wants to execute the critical section. So for that process 2 will request for the token which is already there with process 0. So 2 will send request message on the distributed environment. Process 2 does not know which process is holding the token currently. So it has to send the broadcast request to all the nodes or all the processes which are running into the distributed environment. In that case, Rn request number array will contain 5 flags. Each flag will be there for each process. First flag will be for process 0. This flag will be for process 1, then this is for 2, this is for 3, and this is for 4. Now these processes, process 1, process 2, process 3 and process 4 are not holding the token. So that's why these values are kept 0. Here we can say that the request number will be 1, 0, 0, 0, 0. Total 5 values as there are total 5 nodes. Ln's value, that is last satisfied request numbers value, will be 0, 0, 0, 0, 0. Now queue. Right now inside the queue there is nothing because process 0 is holding the token and nobody has yet done request for that token. If some other process does request for the token, then obviously that process number will be inserted inside the queue. If we are saying that process 2 is requesting for the token, 2 will send the request to all the nodes. Obviously, when the request will be received by node number 0, then that time the value of 2 will be inserted inside the queue. In short, queue is used for holding the pending request from the process. Now, consider that process 0 has executed into the critical section and it wants to come out of the critical section once the execution is over. So in that case, whatever the request which is there at the front of the queue will be popped out and then the token will be given to that particular process. Suppose Q has done request for the token, then Q will contain the value of 2. Once process 0 completes its execution into the critical section, then the topmost request from the queue will be popped out and then token will be shifted to process. So that is what normally happens. Let's go ahead. Now we consider that initially process 0 is executing critical section. So as process 0 is executing in the critical section, we set the value of the flag and we made it 1. For remaining all flags, value is going to be 0. ln is the last satisfied request. So right now, or there is no process which has went into the critical section. So right now the values or ln array all are zeros. Once the token will be transferred from 0 to some other process, suppose process number 2, the token gets transferred. So that time the value of ln will be 1 for process number 0. It means that this value will be set to 1. Here this 1 shows the request number of process 0 and other values are all are 0. It means that the request number for other processes, that is process 1, 2, 3 is 0 because this process has not done the request for the token. Let's go ahead. Now process 1 and process 2 wants to execute the critical section. Right now the token is there with process 0. So process 1 and process 2 have to broadcast the request message into the distributed environment. Initially we discussed if a process wants token, it has to broadcast the request message into distributed environment. The reason behind broadcasting the message is that as the processes don't know which other process in the distributed environment is holding the token, so that's why they need to send a broadcast request so that the request will be received by all the processes into the distributed environment, including the one which is holding the token. Now the request message will contain two things. The first one is process number and second one is incremented request number. So suppose this is my request, it will contain process number which is represented by I here, and it will contain request number of I, okay, and that request number will be incremented request number. So let us see what that incremented request number is there. Now suppose in the above environment, if process 2 wants the token, then process 2 will broadcast the request message on the network by sending the request message as request, and the process number is 2 and Rn of 2, but this Rn of 2 will be the incremented request number. So right now Rn of 2 is 1, right? So we are going to increment the value of Rn of 2 and then we are going to put it inside the request. So 0 plus 1 is going to be 1 here. So request message will be request process number 2 and Rn of 2 is 1. So this request message will be broadcasted on the network. So in short, we can say that request message will contain two things. First one is process number and second thing is incremented request number. If process 1 is sending the request message, then this is what process number and this is Rn of 1. Rn of 1 in this case is 0 here. Rn of 1 is 0 here, but we want to increment it by 1. So 0 plus 1 is going to be 1. So that 1 we have written here. So that is how the request message work. Let's go ahead. After receiving request message by all the nodes or the processes, the following thing happens. Now we know that site number 1 and site number 2 has done the request for the token. So two requests will be broadcasted on the network. So when the request message will be received by other nodes, they will find out these values and they will change these values. So Rn of 1 is going to be 1 because earlier this value was 0 and when request message is sent, that value is incremented. So the new value will be updated over here, and similarly for Rn of 2, the new value, updated new value will be 1, so that value will also be updated here. All nodes will receive the request messages, so at all nodes these values will be updated. Now one more change is going to happen in this case. Look at the queue. Two nodes or two sites has done the request for the token. So inside the queue, request of first site and request of second site will be stored according to its timestamps. If process 0 has already completed its execution inside the critical section, then process 0 will check the front element of the queue. It will pop that element from the queue. In this case, two elements are there in the queue, 1 and 2. So two requests are there from process number 1 and process number 2. So one element with the front of the queue will be deleted and the token will be transferred to process number 1. So let's go ahead. Now the new situation in the distributed environment is shown in this diagram. Token will be there with process 1. Process 0 has already completed its execution inside the critical section. So the content of the Rn is 11100. Content of ln is now changed to some extent. Now it is showing ln of 0's value. It means that ln for process 0 is going to be the last satisfied request number. It means that process 0 has already done execution inside the critical section. And then queue. Earlier there were two parameters in the queue, 1, 2. So out of that now process 1 is holding the token. So that's why we have deleted the value 1. Now only one pending request is there inside the queue, that is for process number 2. Now consider that process 0 and process 3 does the request for the token. When process 0 and process 2 does request for the token, following changes will happen. Earlier the value of Rn here was 1. When the new request will be sent by process 0, obviously the Rn's value will be incremented as we stated earlier. So the value is going to be 2. Process 3 is also sending a request because it is also interested into executing the critical section. The earlier value for process 3 was 0 in the request number array. It will be incremented by 1. So process 3, Rn of 3 is going to be 1. Now process 0 and process 3 are requesting for the token. So these requests should get accommodated inside the queue. So that's why process 0's request will be there inside the queue and process 3's request will be there inside the queue. In this way, the content of array Rn, that is request number array ln, that is what last request executed, and the content of queue will get updated. After executing inside the critical section, process 1 will release the token and it will be returned to process 2, as process 2 is at the front of the queue. Let's go ahead. Now the token will be transferred to process 2. So the content of Rn at process 2 is going to be 21110. As we know that 2 is the number of times request is done by process 0. 1 is the number of times request is done by process 1. Here the number of times request is done by process 2 and number of times request is done by process 3. Now the content of ln array will be 1, 1, 0, 0, 0. These two ones shows that node 0 and node 1 have already executed the critical section. And the content of the queue will be, earlier it was 203. Now as the token is already transferred to process number 2 and the content of the queue will be 0, 3. Same value of Rn will be available at every process which is getting executed into distributed environment. In this way, the process will be repeated and the token will be passed from one process to another. So this is what the Suzuki Kasami algorithm, where the sites may work into distributed environment. The site which is having token will execute the critical section. Other sites which are not having the token and which are interested into executing the critical section need to wait for the token. Once they get the token, then they can execute the critical section. That's it from this particular session. If you are having any doubts, any queries, kindly post it inside the comment section. If you like the videos, please press the like button and subscribe my channel. Thank you.